In the chapter Superposition of Harmonic Oscillations, today we are going to start a new concept of Lissajous figures. Actually, the concept of Lissajous figures is a very important concept in physics, particularly in waves and oscillation. Okay. So, how these Lissajous figures are constructed in different conditions, we will learn. We will also learn what are its applications, but later on. In this present lecture, our aim is to discuss the simplest case for finding the Lissajous figures. And that is actually the case of finding the resultant of two simple harmonic oscillations at right angles when the frequencies of the two SHMs are equal, but their amplitudes and phases are different. Okay? Actually, you will see that actually the shape of the Lissajous figures depends on the frequency of the superposing oscillations. It also depends on the amplitude and phase difference of the two oscillations. Okay? So we will actually consider different situations, but this is the first lecture on it, so it will be the simplest case. So first of all, definitely you have to query that what is this Lissajous figures. Actually, if you want to define the Lissajous figures in a simple manner, you can say that Lissajous figures, which are also known as Lissajous curves or Lissajous patterns, these are actually the graphical representation of the complex harmonic motion. The complex harmonic motion, which is actually resulted from the superposition of two simple harmonic motions acting at right angle to one another. So in fact, when an oscillator or a particle is acted upon by two restoring forces, let us say F1 and F2, and this F1 produces SHM in X on the X line, and this force F2 produces SHM on the same particle on the Y line. So these two oscillations are perpendicular to one another. In this condition, when the particle is acted upon by these two SHMs acting at right angles simultaneously, then the particle neither moves along the x-axis nor along the y-axis, but its motion takes place in this xy plane. But in this xy plane, what will be its actual path of motion? That actually depends on the phase difference and the ratio of the frequencies of the two SHMs. Okay? So for different phase differences and for different frequency ratios, the path will be different. The path generated by the particle under the action of these two simple harmonic oscillations acting simultaneously on the particle, that resulting path traced out or described by the particle is actually called Lissajous figure. If the particle traces a straight line, Lissajous figure will be a straight line. If it traces out a circle, the Lissajous figure will be a circle. If it traces out an ellipse, the Lissajous figure will be an ellipse. So actually, when the particle is acted upon simultaneously by two simple harmonic motions acting at right angles to each other, then the resultant path traced out by the particle is called Lissajous figures. Okay? And as I have told you that actually the shape of the resultant path, or you can say the shape of the figures, depends on the time period, or you can say frequency of the two SHMs. It also depends on the phase difference between the two SHMs and the amplitude of the two SHMs. Okay? So these are the factors on which the shape of this Lissajous figures depends on. In fact, when you talk about the two SHMs, actually these two SHMs may be mechanical, as we consider in this chapter mechanical oscillations, which can be produced by using two tuning forks. Okay? Or it may be alternating voltages, okay? Alternating voltages, which may be produced by electrical AC sources. Actually, when the two SHMs are either mechanical or the alternating voltages and act simultaneously at right angle to each other, then the resulting motion is known as Lissajous figures. Okay? In fact, as I have told you that we will have different type of Lissajous figures that will be determined by three factors. What is the ratio of frequency or time period of two SHMs? What is the phase difference between the two SHMs? And what are the amplitudes of the two SHMs? These are the factors which will determine the shape of this Lissajous figure. Okay? In fact, the idea of this Lissajous figure is very important in physics, because it is used to determine the frequency and phase relationship between two signals, to calibrate oscilloscopes and other measuring devices, and to visualize the behavior of oscillatory system. So these are its applications or its usefulness, okay, which we will learn after the theoretical aspect. Okay. Now, to analyze this the concept of Lissajous figures, we will consider actually different cases. In first situation, we are going to see how we can find the Lissajous figures analytically when the ratio of the frequency of two SHMs is 1:1. It means when the superposing SHMs have equal frequencies or equal time period, although their amplitudes will be different, their phases will be different, but frequencies or time periods are same. Then how we can analyze the superposition of two SHMs acting at right angle on a particle? So for this, let us consider there is a particle, let us say at point O, and it is acted upon by two restoring forces. Let us say that this F1 is the restoring force, which when act upon only on this particle, then it will provide SHM to this particle on this x-axis. Okay? And when the another force F2 acts on this oscillator independently, that is F1 is absent, only F2 acts, then let us consider that due to this restoring force, our particle executes SHM on this y-axis. Okay? Now, when F1 and F2 will act on the particle simultaneously, then our particle will experience two SHMs simultaneously, one along the x-axis and other along the y-axis. Okay? So in this condition, what will be the actual path of motion, which is called Lissajous figures? Our aim is to decide it. Actually, there are two methods to determine it. First one is called analytical method and another is called graphical method. Here in this lecture, we are going to see the analytical or mathematical method to find the Lissajous figures in these conditions. Okay? And for this, let us write the equation of motion of the two SHMs. For simplicity, we consider that the equation of motion of the SHM along x-axis is x equal to a sine omega t. You know, here a is the amplitude of this SHM and omega is its cyclic frequency, and this factor omega times t, this is called phase of the SHM. Here I have considered that phase constant is equal to 0. Okay. Now the another SHM which is along y-axis, that is represented by the equation y equal to b times sine omega t plus phi. Here phi is the phase constant, and you can see that the phase of the second SHM at time t is omega t plus phi, and that of first one is omega t. So what is this phi? Phi is actually omega t plus phi minus omega t. It means this is actually the phase difference between these two SHMs. Okay? And amplitudes A and B are different in general. Okay? Now, you know, our aim is to know when the laws of motion of the particle is governed by these two equations, what will be the equation of motion of the trajectory described by this particle. You know, whenever you talk about equation of trajectory, that means you have to find y as a function of x. This is called equation of trajectory. How y varies with x, how y is related to x, that equation is called equation of trajectory. But here you can see x and y both depend on time t. So definitely to get the equation of trajectory, we have to relate y with x, but after the elimination of t. So we will relate to x and y in such a manner that equation does not contain the third variable t. Okay? So you have to eliminate the variable t to get the equation of trajectory. And how we can do it? This is very easy. You can see this second equation you can write in this manner: y over b equal to sine of omega t plus phi. Now expand this sine omega t plus phi. You know, sine omega t plus phi can be written as sine omega t times cos phi plus cos omega t times sine phi. Okay. Now in this equation, our aim is to remove sine omega t and cos omega t and bring x here. That can be done by the use of equation 1. You can see from equation 1, we can write sine omega t is equal to x over a. But our equation also contains cos omega t. So let us find the value of cos omega t in terms of x. You know, cos omega t is given as a square root of 1 minus sine square omega t. But sine omega t is x by a, so when you will substitute its value, your result will be cos of omega t is equal to a square root of 1 minus x square over a square. Okay? So in this way, we have obtained sine omega t and cos omega t in terms of x. Okay? Now let us substitute the values of sine omega t and cos omega t in this equation number 3. Okay? Let us substitute. You can see after substituting it, our result will be y over b equal to x over a times cos phi plus a square root of 1 minus x square over a square times sine phi. Okay? Now we will recast this equation in a simpler form, in a standard form. And for this, let us bring this first term in RHS in LHS. So our equation will become y over b minus x over a cos phi equal to a square root of 1 minus x square over a square times sine phi. Okay. Now for removing this square root, let us square this equation both sides. So after squaring, you can write y over b minus x over a cos phi whole square equal to 1 minus x square over a square times sine square phi. Okay. Now let us expand the LHS. You can see this will be y square over b square plus x square over a square times cos square phi minus 2xy over ab cos phi. And the RHS can be written as sine square phi minus x square over a square sine square phi. Okay. Now let us bring this term containing sine square phi in LHS and associate with the term x square over a square cos square pi. So our result becomes y square over b square plus x square over a square times cos square phi plus sine square phi minus 2xy over ab times cos phi equal to sine square phi. But you know, this cos square phi plus sine square phi, this is equal to 1. So this equation can be written as y square over b square plus x square over a square minus 2xy over ab times cos phi is equal to sine square phi. This is actually the resulting equation of motion, or you can say that this equation, you can see, does not contain time t, but it relates the variable x and y. Okay, and so this equation represents the equation of trajectory. What path the particle will describe under the action of two simple harmonic motions acting at right angle simultaneously, having same frequencies and phase difference phi. That path is described, or that path is defined by this equation. If you will see this equation seriously, you can say that this is general equation of an ellipse. General equation. Okay. So in general, you can say that the particle in this condition will describe an ellipse in general. But for different values of this phi, which is actually the phase difference between two SHMs, the path will be different. So let us analyze now the different situations. First of all, we will see when phi is equal to 0. When phi is 0, it means both the SHMs are in same phase. Okay? No phase difference. Then what will be the path of motion? We will now see. You know, when phi will be 0, sine phi will be 0 and cos phi will be 1. So in this condition, what will be the equation of trajectory of the particle? For this, let us substitute this value of sine phi equal to 0 and cos phi equal to 1 in this resulting equation A. Instead of cos phi, now we will write 1, and instead of this sine phi, we will write 0. So our equation A now becomes y square over b square plus x square over a square minus 2xy over ab equal to 0. And this can be, written as y over b minus x over a whole square equal to 0. And if you will take this 1 over a, this 1 over b as 1 over b square as a constant common factor, this result will be y minus b over a times x whole square equal to 0. Now you can see this equation, which I have numbered as 1, this equation actually represents a pair of coincident lines and coincident straight lines whose equation will be y equal to b over a times x. Okay, because y minus b over ax will be 0, so y is equal to b over a times x. Actually, you know, this is equation of a straight line passing through the origin, y equal to mx. In this form, this equation is. Okay, and the slope of this straight line will be what? This will be equal to m. At the place of m there is b by a. So if this straight line makes an angle theta with the x-axis, then tan theta, which is slope, that will be equal to b over a. And so the inclination of this straight line is tan inverse b by a. B by a. Okay. So you can say, see this figure, that in this condition, actually the resultant motion of the particle will be a rectilinear motion. Okay, and it takes place along the diagonal of this rectangle, as you can see in this figure. Okay, along the diagonal AB, and actually the sides of this diagonal will be 2a and 2b. You can see, if you take the origin of the coordinate system at O, then this at the coordinate of this point will be plus a, coordinate of this point will be minus a. So this side length will be equal to 2a. Okay, and coordinate of this point, at this point y is equal to b, and at this point y is equal to minus b. Okay, and so the another side of this rectangle is 2b. Okay, so the resulting motion of the particle in this condition is along the diagonal AB. Okay, which is the diagonal of a rectangle having side lengths 2a and 2b. Okay, in fact, you can see from this equation that x and y will have same sign always. It means when x is positive, y is also positive. And you know, x and y both are positive in first quadrant. So this straight line OA lies in the first quadrant. But when x will become negative, then y will also become negative. Such a point will lie in third quadrant. So this line will also lie in third quadrant. So actually, when phi is equal to 0, then immediately you can see from this equation, if we will take phi equal to 0, our equation will be x equal to a sine omega t, okay, and y equal to b sine omega t. So you can see from here that y over x is simply equal to b over a, and y equal to b by a times x. So taking phi equal to 0, you can immediately get the equation of the straight line, which is phi equal to 0, which is actually y equal to b over a times x. Okay, and from this you can now find the direction of motion. You can see from here, when we will take t equal to 0, then sine omega t will be 0, and therefore both x and y will be 0. So at 0 time, the particle is at this point O. But as the time increases, the value of omega t will increase, and which implies that value of sine omega t will increase. And when this omega t becomes pi by 2, then sine omega t will be equal to 1, and x will be equal to A and y will be equal to B. And this is the coordinate of this point, A and B. So the particle moves from point O to B. Okay. But after that, with increase of time, the value of omega t decreases. And when omega t becomes pi, then again sin omega t will be 0 and both x and y will become 0. It means the particle returns back from A to this point O. When it returns, when omega t is equal to pi. And after that, you know, if omega t now is greater than pi, then the value of sin omega t will be negative, and therefore both x and y will be negative. And when this omega t will become 3 pi by 2, then sin omega t will be equal to -1, and this particle will reach to this point B, whose coordinates are -a, -b. Okay. But after that, again the value of sin omega t will increase with increase in time, and finally it becomes 0 at omega t equal to 2 pi. So you can see in a complete cycle how the particle moves. The particle moves from O to A, okay, A to O, and after that O to B and B to O. So in this way, the particle retraces this straight line AOB. Okay? The particle retraces this straight line. Which straight line? AOB. Okay? So in this condition, the Lissajous figure is just a straight line. Actually, if you have studied the chapter polarization in optics, then there you see that a polarized light may be linearly polarized, that may be elliptically polarized, that may be circularly polarized. What happens in case of linearly polarized light? The situation is just like this. So this represents what in optics is called linearly polarized vibrations. So when phi will be 0, the situation is just like linearly polarized vibrations or linearly polarized light. Okay? So I think you have now a clear-cut idea that what will be the Lissajous figure in case of phi equal to 0. Okay? Now we are going to see another case when we will take phi equal to pi by 4, that is 45 degree. Pi equal to pi by 4. When you know pi is pi by 4, then cos phi and sin phi both will be equal to 1 over root 2. Okay? So now we will substitute 1 over root 2 instead of cos phi and sin phi in this resulting equation which we have obtained here in A. Okay? So now substitute 1 over root 2 instead of cos phi and sin phi in that very equation. And after that we will get y square over b square plus x square over a square minus 2xy over ab times cos phi, but now cos phi is written as 1 over root 2 and equal to sin square phi, but sin phi is also 1 over root 2. So this is a square of 1 over root 2. So now this equation becomes y square over b square plus x square over a square minus root over 2xy over ab equal to 1 by 2. This is the resulting equation of motion, or you can say the equation of the resulting path of the particle when the phase difference between the two superposing simple harmonic motions is equal to 45 degree. If you will see this equation seriously and you have an idea of mathematics of ellipse in your course of coordinate geometry, you can easily say that this equation is actually the equation of an oblique ellipse. Okay, oblique ellipse, as you can see in this figure. Okay, so in this condition, the particle will trace out an oblique ellipse, and this ellipse will be described in anti-clockwise sense. You can check it when you will take phi equal to pi by 4. The particle will move along this oblique ellipse, and this rotation of the particle or this motion of the particle will be counterclockwise. Okay, so this is just like an elliptically polarized light, and so it is also called elliptically polarized vibration. Okay. Now, another most important case which we will now consider is phi equal to pi by 2. It means the two superposing simple harmonic oscillations are differing in phase by 90 degree. In this condition, you know, cos phi is equal to 0 and sin phi will be 1. So in this condition, that equation A will become like this. This is x square over a square plus y square over a square equal to 1. This is the well-known equation of an ellipse whose semi-major axis is A and semi-minor axis is B. You can see in this figure here, inside this rectangle again, you can see I have inscribed an ellipse. Okay. So when phi will be pi by 2, then actually the particle will describe an ellipse whose principal axes lie along the x-axis and y-axis. Okay, and the particle will move along this elliptical path. So in this case, the ellipse is traced out in counterclockwise sense. In counterclockwise sense. Okay, and this is just equivalent to what is called in optics left-handed elliptically polarized vibration. Left-handed, counterclockwise sense. Instead of counterclockwise sense, you can say left-handed elliptically polarized vibration. Now in this case, if we impose an extra condition, phi equal to pi by 2 is at ease. Now if you consider that the amplitude of the two vibrations are equal, that is A equal to B, then what will happen? Then you can see the equation of path will become x square over a square plus y square over a square equal to 1, and that is x square plus y square equal to a square. Again, you know, this is the well-known equation of a circle whose radius is a and the origin of the coordinate system and the center of the circle is at the origin of the coordinate system. Okay, as you can see in this figure. Okay, so in this condition, you can see that if two simple harmonic motions having equal amplitude which are at right angle will get superposed, then the resulting motion will be a circular motion. Okay, and you can say that two harmonic oscillations at right angles to each other of equal amplitude and equal frequencies but with phase differing by pi by 2 are equivalent to a uniform circular motion. Okay, and the radius of the circle will be equal to the amplitude of the either oscillation. Okay, in a converse manner, you can also say that a uniform circular motion can be resolved into two simple harmonic oscillations at right angles to each other, their amplitude being equal while their phases differ by pi by 2. Okay. In this case, just as in optics, you study the circularly polarized light. So this is just equivalent to what we say in optics, the left-handed circularly polarized vibration. This is left-handed circularly polarized vibration. Okay. Now let us consider the fourth case. And in fourth case, we consider that phi is equal to 3 pi over 4. When phi, that is 135 degree, 135 degree. So when phi 3 pi by 4, then cos phi is minus 1 over root 2 and sin phi is 1 by root 2. So let us substitute these two values in equation A. Then that equation becomes y square over b square plus x square over a square minus 2xy over ab times minus 1 over root 2. And that is equal to a square of 1 over root 2. So this becomes y square over b square plus x square over a square plus root 2xy over ab equal to 1 by 2. Again you can see this equation represents an oblique ellipse as I have shown in this figure. So the Lissajous figure in this condition will be an oblique ellipse as you can see in this figure. And in this case the particle actually rotates along this ellipse in clockwise sense. So this is just identical to the right-handed elliptically polarized vibration in optics. Right-handed. Okay. Now finally we consider the case when phi is equal to pi, that is both the vibrations are just in opposite phases. In this condition, you know, cos phi will be minus 1 and sin phi is 0. So what will be the resulting equation of motion? This will be y square over b square plus x square over a square plus 2xy over ab equal to 0. And so this can be written as a square of y over b plus x over a. Or in another manner you can say that this is y plus b over a times x whole square equal to 0. Again you can see this equation actually represents a pair of coincident straight lines whose equation will be what? That will be y plus b by a into x equal to 0, that is y equal to minus b over a into x. Okay. So this equation due to the square, this represents actually a pair of straight lines which are coincident. Okay. And the equation of this straight line will be y equal to minus b over a times x. You can see when you will compare this equation by the equation of a straight line y equal to mx passing through the origin, you can see that actually these two equations will pass, these two straight line will pass through the origin. Okay. And since the slope of this straight line is negative, this is minus b over a. So definitely these straight lines will lie in the second and fourth quadrant. Second and fourth quadrant, as you can see. Again in this case you can see that the particle will move from O to A dash and then A dash to O, and after that O to B dash and B dash to O in a complete cycle. So actually this straight line A dash O B dash will be traced out by the particle, and so the Lissajous figure in this case will be a straight line. Okay. But here this straight line lies in the second and fourth quadrant. Okay. Now, finally, we consider that when pi is equal to 3 pi by 2, then what will be the Lissajous figure? Actually, in this case, again you can see cos phi will be 0 and sin phi will be 1. And so, the equation A will become x square over a square plus y square over b square equal to 1. Actually, again you can see that this is equation of an ellipse, okay? And this result is same as you have obtained in case 3, but now the motion will be clockwise, not anti-clockwise. So in this case, if you describe an ellipse, this ellipse will be traced out by the particle in clockwise sense. But we have seen in case 3 that in that case, when phi was pi by 2, then the ellipse was traced out by the particle in anti-clockwise sense. But in this case, when phi will be 3 pi by 2, then the ellipse will be actually traced out in clockwise sense, as I have shown it here. You can see. Okay. So in optics, such a vibration is called right-handed elliptically polarized vibration. Okay. So in this way, you can see the sequence of motion for the different values of phi from 0 to 2 pi. Here I have written phi, last case pi equal to 3 pi by 2. But if you will take phi equal to 2 pi, this situation is same as phi equal to 0. Okay. So in this way, you can see that when the ratios of the frequency of the two SHMs acting at right angle is 1:1, okay, but phase difference phi may have any value between 0 and 2 pi, then we get the different Lissajous figure from a straight line to ellipse. Okay. So I think this theory is now has been now clear to you, and in the second lecture we will see same problem, but in that case you will consider that the frequencies are not equal of the two SHMs, but they are different. Okay, thank you very much.